Okay, good morning, everyone. It's really exciting time, right? We are entering a new era for space exploration. Take the moon as an example. You probably heard about, we have this Artemis mission of sending astronauts to the moon again, right? When was the last time any human beings went to the moon? That was during Apollo times, like over 50 years ago. So in addition to this Artemis mission about sending astronauts to the moon, and there are actually about 200 missions planned for the next decade to explore the moon only, right? And then, this session is related to, like, say, robotics, and then, during the Apollo times, we could already go to the moon, right? All this positioning and navigation was already solved, right? And fast forward, like 50 years later now, given there are so many activities and then so many new advances in computing and the technologies, I can foresee there are these following 4 trends, right? So if you only need to send one, or 2 astronauts, right? You don't need like a lot of structures. You need some structures, but you don't need a lot of infrastructures to enable that. But now, thinking about it on Earth, right? And then we have GPS because that provides positioning for anyone and anywhere on Earth, right? And then if you need to have so many things on the moon, like in addition to astronauts, equipment, robots, solar poles, and then all these, right? And we need to build the infrastructures, such as we want to build like Wi-Fi on the moon, we want to build the GPS on the moon, power plants, base stations, and all these. And then secondly, if you have all these different entities, like people, equipment, robots, right? And then we should explore something like a collaborative intelligence. So because a person is not working on its own, a robot is not working on its own, right? And then maybe related to that, there could be swarm robots or satellite swarms. And then the third part is about long-range autonomy. So far, all the rovers to the moon or the Mars is just a short range, right? They explore a small area. And then we really want to explore, and most of them are piloted by engineers on Earth, right? So we want to enable autonomy, and what's more, we want to enable this long-range autonomy that can allow the robots to be present on the moon, on Mars for a longer period of time and longer distance. And third one, right, is AI for space. I came here like from the early morning part about the keynote, right? The 2 keynote speakers, they both talk about AI, right? So for my research group, I'm just giving you 4 examples, 1 example for each category about what we are doing for academic research group. Right, and then the first one, in terms of infrastructure, we are actually part of this effort of building a GPS on the moon. And then second is research collaboration with NASA JPL. Actually, early on, Tim from NASA JPL for the keynote, he mentioned about the CADRE mission. So this is the very first tech demo of sending a swarm. They call it the swarm of 3 rovers on the moon. So as the first effort having this collaborative multi-rover navigation on the moon. And then the third part is about long-range autonomy, and this is in collaboration with a different group with NASA JPL. This is about the endurance mission concept, right? This mission concept is called endurance because it's really long range, traversing about 2,000 kilometers in the South Pole area of the moon. And then finally, it's about AI. And then we actually, as one example, we are trying to build this neural moon surface maps. And then related to that, we also recently, our research group, we participated in the NASA Lunar Autonomy Challenge. We fortunately won first place for that. Okay, speaking of the time, let's just go dive into that. GPS for the moon. And then when I normally talk to, maybe probably not this audience, but just regular people say, oh, we're trying to build a GPS for the moon. And people thought I was talking about science fiction. But this is real. I think that's a really fun thing, right? So in this group, right, we work on space. A lot of things, science fiction, like Brian's talk, I was really impressed, right? But we are actually, this is real, right? We are actually doing that to enable this to become a reality. So LunaNet is this satellite network. Basically, it's the GPS for the moon. There are satellites orbiting around the moon and to provide communication as well as navigation. Similar to GPS, or the more general word is called the GNSS, Global Navigation Satellite System. This LunaNet is also a system of systems. So as you can see, right, it's a joint effort by US NASA, European ESA, Japanese JAXA, and recently Korea and India, they also want to join this effort. So NASA, like, they are building this basically like a GPS-like system, right? And then European Union, for the Earth users, there's something called the Galileo, right? Similar to the US GPS. And then, so here, like the European Union for the moon, they building something called the Moonlight. So each nation or entity, they are actually building their own constellation for the lunar navigation and communication. But together, they also want to make their system interoperable. So together it's called LunaNet. And then for my research group, actually from 5 or 6 years ago, we started to work on this, right? And at that time, we want to answer this question: can we have a GPS-like system for the moon, but with much lower cost, right? The answer is yes, because we can use smaller satellites as small as a shoebox, versus for the terrestrial GPS satellites, they're pretty big as a truck. And then for the terrestrial GPS, it's expensive because they use atomic clocks. Because if you want to do really precise positioning and timing, you need to know have good clocks on board, right? And then so they use this very expensive, high quality atomic clocks on the GPS satellites. What's more, for redundancy and then robustness, they require not just one atomic clock, but 3 per satellite. So this is just for GPS itself. It's about 100 atomic clocks, or like orbiting in the medium Earth orbit. But for this LunaNet, we want to have cheaper clocks, like over 1,000 times cheaper than the terrestrial GPS clock. And then we have some research paper to show that this is actually doable, because given that we do have the terrestrial GPS, so we can use a terrestrial GPS for the lunar navigation, satellite clock, and ephemeris corrections. And this is not an easy task, because here you can see in this animation, this is in the moon inertial frame, right? And then all the colorful curves, they are the GPS satellite trajectories. So first of all, the moon is really far away, right? And then the terrestrial GPS was not designed for the moon distance. So your receive signal is already really weak. And then in addition, all the signals coming from kind of clustered together from the same direction. So we call it, they have really bad geometric diversity to enable good positioning. Or we have the technical word called the dilution of precision. So that's make this positioning really hard, right? But is it really possible? We in our lab, we demonstrated, like with simulation, it is possible. And then it was quite exciting that the NASA has this Lunar mission. So just this year, they launched the mission on board the Firefly Aerospace Blue Ghost Mission 1, and then launched on January 15th. And then it catches signal from over 300,000 kilometers away, and then sets the distance record. And then also, very fortunately, that mission was a success. So for some other missions, you may lose the payload, but this was a success. And then this is basically the hardware demonstration showing that you can send a GPS receiver on the moon and then receive the signals and use that for positioning and navigation. I think I need to go a little bit faster. So that's about building infrastructure, right? Setting up a GPS for the moon. Second is the collaborative intelligence. And then for that, we also was very fortunate to have a 3-year collaboration with NASA JPL. It was the multi-agent autonomy group led by JP Lacroix. And then this one is about sending a swarm of 3 rovers on the moon. And then I think given the keynote from JPL team already talk about that, I'll just show our group's contribution. So for this one, our research group, we got this, we call it physical twin of the sensor suite for the CADRE robots. And then we develop algorithms for collaborative positioning and navigation, and then to have this algorithm to be robust against communication loss. And then, the goal for these multiple robots is to traverse this area and then do the mapping of the area, right? And then intuitively, the rovers, they should go together, right? They got released by the lander together, and they should go together and traverse the area. And then somehow after we implemented our algorithm, we show that the rovers, maybe I should pause halfway here. The rovers, instead of going together, maybe you can see, right? They started to get separated, and then they formed this kind of a diamond shape. And then we were wondering why, and then later we realized actually our algorithm, right, is adaptive, and then it's for maximize the positioning and then also traversing the area. So if you think about if all the rovers were lined up, then you don't have good spatial diversity among the rovers, right? If they form this triangular shape, so with respect to, for example, this rover, the other 3 rovers can basically help this rover and provide a better positioning for that rover. And then third example from my group is the long-range autonomy part. And then this is also a really cool mission concept in collaboration with a different group of JPL. And then this is a long-range moon rover, and they want to basically collect samples in the south pole area of the moon. And then this whole distance is about 2,000 kilometers. And then, yes, so it's about this, right? And so ideally, we want to have this LunaNet available for this a long distance traversing, right? Just actually I drove here from Stanford, from San Francisco Bay Area, right? We had to use a GPS. But this one, it will be before the whole LunaNet constellation was available. So what do you do if you need to do this long drive and then autonomously without the GPS, right? So the existing lunar landscape is any mission, there's always a communication satellite. So for this lunar endurance mission concept, there's also this lunar pathfinder satellite, which is going to be launched next year, I believe. And then that provides communication, right? And then, okay, so for traditional way, for desired and traditional scenario is if we have a rover here, we want to have multiple satellites in view. And then each satellite will have the navigation payload and provide the positioning, right? But in our scenario, currently we do not have the whole LunaNet constellation available. We only have a single satellite. And even that single satellite is a pathfinder satellite. It's for communication, not for navigation. So current situation is we only have one satellite and no navigation payload. There's only the communication part. But we realize actually we can still make use of this one communication satellite, given that the rovers are not in a rush, right? So if the rover want to locate itself, just stop here, right? And just wait. And at this time, the satellite was here. After a while, the satellite will move here. And then next, the satellite will be there, right? That's equivalent to you have multiple virtual satellites in view. Okay, so that's cool. So we can have measurements over time. That's equivalent to multiple virtual satellites in view. If we do not have navigation payload, then you can leverage Doppler because you know the trajectory or the orbit of the satellite, right? And then this expected Doppler measurement information, and you can utilize that to do the positioning. And then finally, it's about AI for space. So for my group, we're working on this building a neural map for the moon. And then, so this is coming from the computer vision and computer graphics community. About a few years ago, they have this new way of modeling 3D objects called the Neural Radiance Field and then Gaussian splats. So basically, it's just a way of modeling and then representing the 3D objects or environment. If you think of a map, right, traditionally, you can either have, say, grid-based map or point cloud map. And for this, you can just think about as this map is represented by a big neural network. So the map is basically the layers and parameters of the neural network. And then for that, actually, this neural map has a lot of advantages. One of them was good for rendering. And then, so we actually built this neural, a moon surface map here. And then once you have this really good map, and then you can render the view of the rover. So that means if your rover was here facing this direction, given this neural map, and then you can basically generate what is the expected view from the rover. And then we can actually utilize that for do better moon surface path planning. And then finally, so NASA recently put together a 6-month-long competition called the NASA Lunar Autonomy Challenge. And then I think early on from Brian mentioned about you want to set up this in the South Pole area, right? For the navigation part, there are a lot of challenges. For example, you can see these long shadows for the south moon part of the area. So if you just use like off-the-shelf, a lot of the algorithms for say vision-based navigation or some other things, it just won't work. So NASA actually, they did this really nice high-fidelity simulation environment, and they set up this Lunar Autonomy Challenge. And then the challenge finished in May this year, and then our group was very fortunate to win the first place in the NASA Autonomy Challenge. And here I can show you. So the challenge is you have a lander here, you have the rover, you have to explore the area, and then the goal of the challenge is to perform the mapping and then positioning of this rover. So as you can see, right, we need to kind of maximize exploring an area, and then we also need to, I think Brian also mentioned about go back to the lander, right, to check where you are. So we have this kind of a trajectory, like go this way and then this way. And then we have a different kind of AI, and then a combination of AI and a model-based method for the mapping and positioning. Okay, I think that's all I want to say today. Basically, it's a really exciting time for spatial exploration. And then because I lead the navigation lab at Stanford, so from the navigation point of view, right, when you have to basically navigate or like have so many entities, say, on the moon surface, then we need to start to building infrastructures, such as building this GPS for the moon. We need to leverage collaborative intelligence, such as the CADRE mission of sending 3 small rovers on the moon to have this collaborative navigation. And we need to start to think about the autonomy, especially about the long-range autonomy, such as this endurance missions concept of having this sample return, for a rover to traverse 2,000 kilometers in the South Pole area for the moon. And finally, there's so much AI can do for space, and then it's still unexplored. So I showed this one example of building this neural moon surface map, as well as our participation in the recent Lunar Autonomy Challenge. Thank you so much.
Thank you for that excellent talk.
Question at the end, right?
Yeah, we can have one quick question.
Yeah.
One quick question. Yeah.
This is such a good talk.
Yeah.
I was wondering for the autonomy challenge, is the pathway pre-planned, or is it something that changes every single time you run the rover? I'm just kind of curious on that.
Yeah. The pathway is so the general like a rough pathway is pre-planned, but we also have the onboard camera. If say there's a rock, right? You like roughly you should go this way, but if there's a rock here, you have to diverge. We also have the mechanism. Sometimes even if you have the onboard, but there's like uncertainty also about the onboard perception. So sometimes the rover may just basically get stuck because there's a rock, and then we detect that, we actually back the rover, and then we try to go around. We have that as well. Yeah. Good question. Thanks.